So let's go ahead and do a couple of examples. So this is problem 32 from your textbook, and this is to just give you some intuition about how strong or weak this gravitational force is. So imagine you've got two objects, and they're each 5 kilograms. So they have the same mass, and they're separated by 15 centimeters is separated by, so that's what, 0.15 meters. And the first thing I want to know is what's the force between these two objects. If I were to release them and they just experience the gravitational force from themselves, how fast would they be going when they hit? And we're going to assume that these are point sources, so we don't have to worry about how big they are when they hit. We'll just assume that they're small relative to this size here. Okay, so let's first start by looking at the force to get an intuition for how big or small this is. So the force is equal to G m1, which is just m, times m2, which is just m over r squared. And that's going to be equal to my gravitational constant, 6.67 times 10 to the minus 11, and then I get 5 and 5 kilograms, and then this is all divided by 0.15 squared. So that's 6.67 times 10 to the minus 11 times 25 divided by, let's see, 1.5 squared is 2.25, and then I get an extra factor of 10 to the minus 2 in there, right? Because that's 10 to the minus 1. So I can go ahead and cancel these things out. This is 2.5 times 10 to the 1. So I'm just going to assume those are about the same since I've just kind of one order of magnitude here. So I'm going to get something like 7, make that 7 times 10 to the minus 11. Plus 1 is 10. Minus a minus 2 is another 2 factors. So this is going to be 7 times 10 to the minus 8 newtons. So this is a very small force. Although you'll find from your homework that compared to the force of gravity of, say, something like Jupiter on you, it's pretty big. Okay, so now let's look at the other question, which is how fast are these going to be going if we let them go? So let's do this from an energy perspective. So from an energy perspective, I'm going to look at the initial potential energy. And the potential energy is going to be between these two objects. So I've got one object here, one object here. I've got the distance between them. And I'm just going to worry about the magnitude of this. So the magnitude of this is G m over r. Okay, so that's going to tell me the amount of energy that I have stored in these two objects. So when I let them go, they're going to go ahead and convert that to kinetic energy. So my final kinetic energy is going to be these two objects moving when they hit each other, and so we'll say that that's 1/2 mv squared for the first one plus 1/2 mv squared for the second one. They'll move the same distance because they're the same mass, so this is just mv squared. So I'm going to set those equal to each other. I get G m over r is equal to mv squared. And so I'm going to get v is equal to the square root of G m over r. And if I go ahead and calculate that out, I wind up getting something like 5 times 10 to the minus 5, which is small, meters per second. That's small, but not 0. And if you imagine 5 times 10 to the minus 5 meters per second, that's like 10 microns per second. But that means over quite a few seconds, you can still move. And these weak gravitational forces actually do have an effect on things like asteroids and other debris in our solar system.